This one is my 6th lecture session in which I am going to present the series operation of SCR. Before going into my session, first we need to know which purpose we are using the series operation and for which purpose we are using for the parallel operation. Actually, SCR itself a power device or power switch which can be implemented for anywhere for power circuit for designing purpose of converter. That is why the specification of the SCR in terms of voltage and current is very important to understand. Suppose we are applying a huge number of voltage across SCR, but the specification is not be allowed for that amount of voltage. Then the so many SCR should be connected in series and which will form a string. Suppose we are applying a huge amount of current across SCR, then the SCR is not permit that amount of current, then we should connect the SCRs in parallel. That is why for high voltage application, they should be connected in series, and for high current application, they should be connected in parallel. So today I am going to discuss about the first topic, that is the series operation of SCR. Okay? Here we consider two identical SCR are connected in series. That is why we are going to demonstrate the topic, that is series operation. Okay? When system voltage is more than the voltage ratings of single SCR, then SCRs are to be connected in series in a string, where at beginning, consider two identical SCRs are connected in series, and we have shown here the VI characteristics of them. That is why we consider the SCR 1 and SCR 2, both are connected in a series string, and the string current is suppose I0. That is why the voltage appearing across the first SCR, that is suppose V1, and the voltage is appearing across the second SCR, that is suppose V2. That means we can draw the VI characteristics of the both cases. Suppose SCR1, in case of SCR1, the breakover voltage is suppose VBO1, and for SCR2, the breakover voltage is suppose VBO2. We consider in case of the SCR1, the leakage resistance is suppose V1 by I0, and the leakage resistance for the SCR2, that is suppose V2 by I0. Normally we assume in the first SCR which has a high resistance path, and in case of the second SCR which has the low resistance path. That is why considering this resistivity of this particular SCRs, we can plot these VI characteristics. This dotted line defined by the SCR1 characteristics, and this the straight line which is defined by the SCR2 characteristics. So from these characteristics we can see that is each thyristor is related to the forward biasing voltage, that is V1, which is less than the forward biasing voltage, that is forward breakover voltage VBO1, and for SCR1, and VBO2 for SCR2. So it is clear that for the same leakage current I0, two thyristors can support maximum voltage, that is V1 plus V2, not that is 2V1. So we can define the string efficiency, that is equal to actual voltage of the whole string divided by individual voltage of the SCR multiplied by the number of SCR which is used for a single string. That can be defined by V1 plus V2 by 2V1, that should be equal to 1 by 2, 1 plus V2 by V1. That means it will give us the result always less than 1. So from this figure we can say at the conducting time SCR1 and SCR2 which will not protect or cover the same amount of voltage. That is why it is possible to say SCR1 will be triggered first, then the question is SCR2, because in any case of the string, suppose SCR1 is connected directly to the power supply, that means maximum voltage stress that can depend on SCR1. That is why if SCR1 will be fired first, then the question for SCR2, that is not required for the application purpose. Our approach, we are trying to turn on the all SCRs at any instant. That is why the potential difference across the all SCRs should be same. That can be possible by using proper suppose we can connect a proper or particular value of resistance across each SCRs, then we can say the equal potential difference can be occurred for the each SCR of the string. That can be explained in my next slide. See, this unequal distribution of the voltage can be overcome by connecting a suitable resistance across each SCR such that each parallel combination has the same resistance, in which we can say the potential difference across the SCR will remain same. This will require the different value of resistance for each SCR, which is very difficult to identify. So, to obtain a uniform voltage distribution during steady state working, same value of shunt resistance will be connected across each resistor as given below, and this is why we can design the particular value of resistance value. Suppose here we assume this is a string in which we are connecting the n number of SCRs. This is SCR 1, SCR 2. In this way, this is n number of SCRs are connected. And suppose in case of the first SCR, the leakage current is suppose IBMN and the resistance R is connected over here. The same amount of resistance is connected across each SCRs of the string. I don't know what is the exactly value. That will be calculated later. Anyways, see, that means if we consider the string current is I, that means I1 starts flowing across R and the IBMN, the leakage current is flowing across the first SCR. If this leakage current is permitted by the first SCR, that should be permitted for the second one. That is why same amount of leakage current, that means the string current I is just flowing across the second, next year and onward. That means we can say, we assume in case of the next parallel combination or shunt combination, the current I2 is flowing across across R. Similarly, this is I2R. That means we can say in the first case, suppose first SCR with leakage current IBMN and all other SCRs which is having the leakage current suppose IBMX, means the same amount of leakage current that is possible for the other SCRs. But we assume for the first SCR which can block the maximum voltage, that is why the leakage current we assume the different value, that is IBMN. Okay, and the potential difference or voltage appearing across the first SCR, that is suppose VBM. Okay, so from this schematic diagram, let SCR1 has minimum leakage current that is defined by IBMN, which blocks voltage VBM, and remaining SCRs, suppose n-1 number of SCRs that can have a same leakage current and which is defined by IBMX. So, from this schematic diagram, we can write I1 equal to I minus IBMX and I2 equal to I minus IBMX. So, go to the previous slide. Which one is I1? This is I1. So we can say I1 that should be equal to I minus IBMN, whereas this I2 that should be equal to I minus IBMN. So for n number of SCR, we can replace the equation that is in this way. So for first case, for first SCR, that is I1 equal to I minus IBMN, and for the next or the other SCRs which is having the equal means leakage current, that can be defined by I2 equal to I minus IBMX. So the voltage across the first SCR, that is given the circuit diagram, that is VBM equal to I1 into R, means the voltage drop across the parallel resistance, that is I1 into R, and voltage across other n-1 SCRs, that can be defined by n-1 into I2 into R. So that can be done by this picture, means that is VBM, that is equal to I1 into R, is a potential drop across this resistance, and for the n minus 1 number of resistance, that can be done by, that is I2 into R. So we can say these two equation like, that is SCR1 VBM equal to I1R, and for n minus 1 number of SCRs, that is I1 n minus 1 into I2R. So from the sting voltage, we can write the expression, the total sting voltage is defined by Vs, that should be equal to total voltage drop across the each parallelly connected resistance. For the first, that is I1 plus R, means this one, and for n minus 1 number of thyristors or SCRs, that is n minus 1 into I2 into R. So after simplification, we can have the result, that is VBM plus n minus 1 R 1 minus IBM m into mx. So again after simplification, we can rewrite the expression VBM plus n minus 1 into R under bracket I1 plus IBM n minus IBMX, where we can identify this one. Because from this expression, we can say I equal to I1 minus IBM. That is why we can replace the part I, that is equal to I1 plus IBMX. Okay, and this is the remaining part, that is same. So again after simplification, we will have the equation, that is VBM plus n minus 1 R I1 minus, we have taken the common term minus, so under bracket that will be IBMX minus IBMN. So after replacing this part by del IB, is a very small amount of current, that is why defined by del IB. So the equation stands for VBM plus n minus 1 R into I1 minus del IB. So we can rewrite the expression again, VBM plus n minus 1 R I1 minus n minus 1 into R del IBM. Just I have multiplied the term in the bracket. That is why after simplification, again we can rewrite the expression like VBM plus n minus 1 VBM minus n minus 1 into R del IB. So we can ultimately, we will have the result, that is NVBM minus n minus 1 R del B. So after simplification, then we can get the exact amount of the resistance value through which we can distribute the equal number of equal amount of voltage across the all SCRs of the string. So this is called actually the snubber resist. This is called actually the static equalizing circuit. Okay. So now we are going to introduce the static equalizing circuit. That means previously we have seen that the voltage was distributed across the each SCR, across each SCR, that was V1 and V2. Okay, V1 and V2. But in this case, after using this particular amount of resistance across each shunt path, we can say then the voltage will be equally distributed across each SCR throughout the string. That is why in this slide we can say, by using this particular of resistance value R, then the voltage is equally distributed, means Vs by 2 and Vs by 2. So this R, this particular design value of R, which I have calculated before, that is NVBM minus Vs divided by n minus 1 del IB. This is called snubber. It was my mistake. This is called actually static resistance or static equalizer circuit. So through which we can distribute the total supply voltage equally across each SCR of the steam. So this is all about for the static equalizer or static equalizing circuit. Okay. But this is not enough for equal distribution of the supply voltage across each thyristor of the steam during turn on and turn off process. Then we are going to design the dynamic equalizing circuit. So in the next slide that will be discussed briefly. First we are going to discuss about the topic on during on, means is a equal voltage distribution during on state or during turn on the SCR. Actually, static equalizing circuit is confined for a particular value of resistance through which we can distribute the equal amount of voltage across each SCR of the string during steady state operation. Okay, but we cannot neglect what will be the voltage appearing across during turn on and turn off. That is why this topic is confined for the dynamic equalizing circuit, or rather to design the dynamic equalizing circuit. So first, that is what happened during turn on. See, we know the two SCR, SCR1 and SCR2 both are connected in a string. And by using that amount of resistance R, now the supply voltage Vs that is equally distributed across the SCR1, that is Vs by 2, and for SCR2 that is again Vs by 2, as the voltage are equally distributed. Now see, we assume this is the string voltage Vs with respect to time axis, and this is the anode voltage of individual SCR with respect to time. So when the string voltage is Vs, then the anode voltage of each SCR, that is Vs by 2, that means this is Vs by 2 and this is again the Vs by 2, that means total supply voltage is distributed throughout the two SCRs, that means this is Vs and this is Vs by 2. Now what happens, see, when the turn on process initiating, then suppose the SCR, we assume, suppose the turn on time SCR2 is large with respect to turn on time the SCR1. Then what happened? And this, the difference between these two turn on, suppose del D, del TD, which is defined by Vs equal to Vs by 2. Sorry, is a string voltage. Means this turn on time is defined by, means how much turn on time is greater in case of the SCR2 with respect to SCR1, that is defined by del TD. Okay. So when SCR1 on, then SCR2 is off. As we assume the turn on time of SCR2 is large with respect to SCR1. That means when SCR1 is turned on, then SCR2 is turned off. Suppose assume SCR1 is turned on. Once the SCR1 is turned on, that means what? That means the voltage across the SCR, that should be very low in magnitude, as any switch when starts working it is behaving like a short circuit. That is why once the SCR1 is turned on, that is behaving like a short circuit. That is why voltage appearing across SCR1 that falls, but not exactly zero, because of, again we must say, due to presence of the 4 layers and 3 junctions. Anyways, that means the total string voltage is Vs. That means once the SCR1 is turned on, the total voltage is appearing across the SCR2, right? Because the string voltage is Vs, that is why the voltage is boost across the SCR2. That is why SCR1 voltage falls, but the voltage across the SCR is boost. Okay. Similarly, we can say in this axis SCR1 fall and say the SCR voltage, SCR2 voltage is Vs. So same up to the point of T1. Okay. Suppose next, after few time delay or few time duration, just I have mentioned before, that is defined by del TD. After del TD, suppose SCR2 will be off. Once the SCR2 will be on. When the SCR2 will be turned on, then the total string voltage is false, as well as as the both SCR starts working or starts conducting, then the string current can easily start flowing throughout the both SCRs. That is why right now we can say the SCR string voltage falls as the both SCR starts working and the SCR current is high enough which can able to share the total string current. Okay, so due to which we cannot explain during turn on time the voltage has distributed properly. By this explanation, again we can see when the turn on process initiating, then the voltage distribution again can differ. That is why the delay time has occurred. Both the SCR will not be turned on at the same instant. Okay, so this can happen in case of during turn on. Now I am talking about for turn off process. Same thing can happen for turn off process also. Okay, see, actually during turn off we know the SCR can be turned off by reducing the anode current below a point that around the holding current. Okay, suppose we consider again, just for explain this part properly, we assume the turn off time for SCR2 is large with respect to the turn off time for SCR1. Okay, and turn off time is defined by the SCR2 is suppose TQ2 and for SCR1 that is TQ1. Okay, that means what? We can represent this part by the turn off process. It has been explained by my previous lecture session. Okay, that means up to this point we can say both the thyristor was in working state or conducting state. Still we are reducing the anode current to a value up to 0. But still there is a moving charges that is inner side still in moving condition. That is why they are both are in conducting state. When the current falls to almost to the holding current, that is the negative biasing applied across the both thyristors, then the first thyristor suppose turn on at the point T1. Okay, and again at the point T2. Then suppose thyristor T2 is still in working state. That is why it will turn off at the point of this point or T2. Means we can say the turn off time for the first SCR that is TQ1 and the turn off time for the second SCR that is TQ2. That is why it can happen, because of when the first SCR is turned off, then the extra amount of charges still that is appearing across the second SCR. That is why the second SCR still is working state. That is why we should give the more negative biasing to turn off the second also. That means we can say during turn off process the voltage distribution across the both SCRs are not same. So what will be the process in which way we can sharing the same amount of voltage during turn on and during turn off? That can be properly explained by this diagram. Actually, during turn on, due to internal capacitance effect or self-capacitance effect, the voltage were not equally distributed. That is why first we should connect a capacitor across each SCR for equal voltage distribution. As we know, the capacitor gets charged very fastly. That is why this capacitor voltage is appearing across SCR. That means every SCR will reach the particular amount of the voltage or same amount of voltage. That is why they can be turned on at the same instant. Okay, but there is a problem. That means when the anode current starts flowing, as the capacitor is there, that is why the capacitor will be charged fast. Okay, that means at the first case, if the thyristor 1 and the thyristor 2 both are in the forward blocking state, that is why small amount of leakage current can be flowing across the string, but as it provides the huge amount of resistance, that is why first the current try to flow first capacitor, then the question for the thyristor, as the current starts flowing throughout the capacitors, that means the capacitor gets charged. Once the capacitor gets charged, that means it tries to discharge in opposite direction. This is the normal behavior of the capacitor. We know the capacitor charging, the direction of the capacitor charging current and the direction of the capacitor discharging current, both are not same. Both are just opposite. That is why if the capacitor will get charged through this direction, that is why it should be discharged through this direction. Once the capacitor tries to discharge across this path, then it will give the huge amount of voltage at a particular instant across the SCR. Then the SCR junctions can be damaged permanently, as the capacitor discharging is very fast. To protect it, we are using this RC resistance because of this discharging part, to limit this discharging current or DIDT current from the capacitor across the SCR. But there has a problem. What if we are adding this kind of the resistance across the in series with respect to capacitor? Then during charging time it will take more current, because the resistance tries to oppose the charging current of the capacitor. That is why we should bypass this current. That is why we are using a unidirectional diode over here. That is why during charging that current starts flowing to this direction, right? And during discharging the capacitor, then it will be reverse biasing condition, then capacitor will discharge through this resistance. That is why discharging current will be limited by this resistance. So this designing part is called dynamic equalizing circuit. That is very important. This is dynamic equalizing circuit. That means by using this kind of dynamic equalizing circuit, we can say as the parallelly connected capacitor is there, they can actually dilute the internal capacitance effect of the SCR, and the voltage will be equally distributed during turn-on process. And previously, I had discussed about the static equalizing circuit that can deliver the same amount of voltage during steady state operation. That means during turn on and during steady state, the voltage will be equally distributed by using these two circuits, that is static equalizing circuit as well as dynamic equalizing circuit. Okay, now I am talking about in case of the turn on process. We know in case of turn off, the SCR should be in reverse bias condition. That means then a reverse recovery current can easily conduct throughout the SCR. Okay. Then what happened? Suppose assume the SCR, the turn off time of the SCR 1 is large with respect to the turn off time of SCR 2. Means SCR 2. That means SCR 2 still in conducting state when SCR 1 is turned off. Then what happened? How it is possible? Actually, see, once the reverse leakage current, the reverse recovery current starts flowing in the opposite direction of the two SCRs, SCR 2 and SCR 2, if the first SCR is blocked this reverse recovery current, then it will be splitted by two components. One is flowing to the resistance which is connected to the static equalizing circuit, and a different component is flowing to the capacitor and the resistance which is connected in case of dynamic equalizing circuit. So why this kind of phenomena can be done for during turn on process? That can be explained in my next slide properly. See, in case of this, when we are trying to turn off the SCRs, the SCR string should be in reverse bias condition. That is why this one is positive, this one is negative. As all the SCRs in a string, there should be in reverse biasing condition. And what happened when we assume the SCR1 has short recovery time with respect to SCR2? The difference of this recovery charges del Q, which is the product of the current and the time. Once SCR1 recovers fast, it goes into the blocking state. Then extra amount of del Q left in the SCR2. does not allow to pass, these extra charges del Q pass through this means the circuit which is shown in this figure. That means what? When SCR1 is recovered first, still it is not recovered because it has some extra amount of charges that can be defined by the del Q. As we know, that is the characteristics curve during turn-off process. T1 for the first turn of the SCR1 and T2 is the time for the second SCR. That means when the first SCR already turned off, then the extra del Q amount of charge which should be stored across this capacitor, due to which the SCR the turn off time of the SCR is large with respect to the SCR1. That means this extra amount of charge that should be stored by this capacitor which is parallelly connected to the first SCR. If we consider a long string where the n number of SCRs are there, that means each capacitor which is connected to the particular SCR, it can able to store the charges which has to be taken from the next SCR. Okay, so we can say in this circuit SCR1 will share highest transient voltage, say VBM. So the voltage across the top SCR V1 equal to VBM, just assume, and voltage across the both SCRs, SCR2, suppose V2 equal to Vm minus del Q by C. That is the voltage. If first SCR that is V1, so second should be equal to VBM minus del Q by C. So we can write the expression of the total string voltage Vs, that is V1 plus V2, and we have taken the value from the above discussion, V1 equal to VBM and V2 equal to VBM minus del Q by C. That means 2Vm minus del Q by C. So after simplification, we will get the result, that is VBM equal to 1 by 2 Vs plus del Q by C. And from the equation 1 that is defined over here, from the equation 1 which is defined over here, we can rewrite the expression, that is V2 equal to VBM minus del Q by C, or 1 by 2 Vs plus 1 by 2 del Q by C minus del Q by C. That means we can modify the expression, that is V2 equal to 1 by 2 Vs minus del Q by C. That means we can say from these two expressions, that is V2, we can have the value of V1 and V2 separately, and the basic difference, that is del Q by C. So if we can add the particular amount of the capacitor which is able to store the extra amount of charges taken from the next SCR, then we can easily contribute the same amount of voltage which will be appearing across each SCR for the string during turn-off process. So this is all about for the static equalizing circuit and dynamic equalizing circuit, and how we can distribute the same amount of voltage across each SCR for a string and series connected SCRs for a string in this way. So thank you for your kind attention, and thanks for investing your valuable time here. Thank you very much.